Hello, this review is going to focus on circles and triangles in particular. So we're looking at lengths of an arc or areas of a sector, as well as for triangles, the cosine rule, the sine rule, and finding the area of a triangle. This is a screenshot of your IB Math SL formula sheet as far as the circular functions and trig goes. One thing that they don't have written on here and is particularly important for this section about length of an arc and area of a sector, r is the radius and theta is the angle of that. Let's say we have a circle and here is our sector. That angle is the angle inside there, and that goes with your area of a sector or with this length of an arc being the length of that piece of the perimeter of the circle. The only thing that is not written here is that theta, for both of these formulas, theta has to be in radians. And so anytime that you are trying to talk about length of an arc or area of a sector, we're talking about pi r squared, area of a circle, or 2 pi r, length of the circumference. Those are all in reference to radian measures. And then over here we have cosine rule, sine rule, and the area of a triangle. Those are all going to be very helpful. With cosine rule, the two times we tend to use that are if we know, let's say, all three sides of a triangle like that, and we're trying to find an angle. And we'd be more likely to use this formula to go with that one. Or if we know, let's say, two sides and we know the interior angle and we're trying to find this side that's across the way, then we're more likely to use this arranged formula for cosine rule. We use sine rule to solve for angles or sides of the triangle when we have a matching set. So for example, let's say we have this triangle here, and we know this is 3 and that this is 20 degrees, and then we also know that this is 7, and we want to find this angle. We can use this because we have this matching set, the angle and the side that is across from it. So that's when we can use sine rule. The other time is a similar situation where, same idea, we might know 20 degrees and 3, but we also know that this is 52 degrees, and we're trying to find this side length. And again, we can use sine rule for this because we have this matching set. So those are the two kinds of scenarios where we use sine rule. And then this area of a triangle formula is great because 1/2 base times height, although it is always correct, it's not always the easiest way to approach the area of a triangle if we don't have a clear base with a clear height that we can see. It sometimes is more useful to use this. Take note that this A and B, those are sides, and C is an angle, right? Lowercase letters are sides, uppercase letters are angles. So in this example, we're talking about a triangle where we know two sides and the angle between them. So A and B would be 7 and 3, and C would be 20. It always, always, always has to be two sides and the angle that is between them. Those are the things that have to fill A and B and C here. So taking a look at our problem, they start us off by asking us to find the length of an arc, and so we want to just fill in that formula. So we have length equals theta times r, and so we want to find the length of arc ACB, so it's talking about this arc right here. And so theta is 1.2. We know that that's in radians because there's no degree symbol, so we're good. Like I said on the last slide, we have to use theta in radians whenever we're working with lengths of arcs or areas of sectors. And then we also know that the radius is 8, so this problem is super straightforward. We're just multiplying 1.2 times 8. So that gives us 9.6. And we should always put a unit, so that would be centimeters, because I see it up there. The radius was 8 centimeters. Okay, the next thing it asks us to do is to find AB, and so that's this length here. So now we're really looking at a triangle, and so we're really looking at this triangle AOB, again, where this is 1.2, this is 8. We also know that O to A must be 8 because that is a radius as well. And so when we look at that, we don't have a matching set of side and angle. What I mean by that is 8 doesn't have the matching angle across from it. 1.2 does not have the matching side length across from it. This side length of 8 doesn't have this angle across from it. All to say that we can't use sine rule. We can only use sine rule if we have that matching set. So we're going to be using cosine rule. So I'm just going to set it up right here. It says c squared equals a squared plus b squared minus 2ab cosine c. Keep in mind that all of those letters are just placeholders. Just make sure that every time you're talking about this side c, if that's the side you're solving for, then this angle must be the angle that is across from this side. And then these two are the other two sides. So we're solving for this side AB. So the angle that's across from it is 1.2. So that's going to go here. And C is what I'm solving for. And so that means that our other two sides, 8 and 8, are A and B. And so when we solve that, we get 81.618 dot dot dot. Make sure that your mode is in radian modes when you're doing this on your graphing calculator. And then we take the square root of both sides to solve for that, and that gives us 9.03 when we round to say 3 significant figures, centimeters. So that's our answer for AB. And then the last part says, hence find the perimeter of the shaded segment. So that's just making sure we know what perimeter means. And perimeter would be the entire length of, actually I already have drawn it in right here, right? This length of arc ACB plus this length AB. And so really all we're doing is taking our two answers, 9.6 and 9.03, and that is just adding them up to get our final perimeter of the shaded segment. So 9.6 plus 9.03, that gives us 18.63 centimeters. Arc lengths and sector problems tend to be very straightforward, but you just have to always remember that theta has to be in radians. Okay, so here's our next one, and I think if you'd like to give it a pause, you should be able to solve at least part A with just what we've done on the video so far, but I will go ahead and work it here for anyone who's not sure really where to begin. And when I look at this, I'm trying to find AC, and I'm going to ask myself if there are a matching set, an angle and the side that is across from it. And we don't have one here. This side, we don't know this angle. This side, we don't know this angle. So we don't have a matching set, and so that's what clues me into the fact that we can't use sine rule. So we're going to be using cosine rule. So again, just like before, it's the same exact formula. And again, just making sure that the side that we're solving for, that we put the angle that is across from it for C. And then the other two sides, doesn't matter which one we call as A and which one as B. And so we go ahead and solve that. And we want to make sure that we're not rounding prematurely. And also make sure that our mode is in degree mode now that we've switched it back. And it didn't, oh, it's centimeters, good, it did give us a unit. So there is our length, AC, and so I'm going to go ahead and add that to our drawing because we're probably going to need it for our next part. So the next part asks us to find angle BCA. So that's this angle. And now when I ask myself, do we have a matching set? The answer is now yes, because we know this angle, 100, and the length of the side across from it. So now we can use sine rule in order to find this angle. So we have angle and side, and then we're going to solve for that last missing piece. So the sine rule is often written, A is to sine of A, equals B to sine of angle B, equals C to sine of angle C. We're not going to use all three of these. We're talking about set B and set C, because B is the set that we know, and C is the set that has the part that we're trying to find. So length B is 12.5. That's the length of the side that's across from angle B. We know angle B is 100. The length of side C is 6, and the length of angle C is what we're trying to find. And so a lot of people like to go ahead and just cross multiply here. That's a fine strategy if you'd like. And then we're going to divide both sides by 12.5. And so we get sine of C equals 0.4727 and so on. I'm going to use that whole answer when I take sine inverse of that number. So that's how I get C, angle C by itself. And that's on your graphing calculator. 4727. And when I do that, that gives me that C is 28.2 degrees. Now the only trick is, anytime that we are using sine rule to solve for an angle, we always need to double check if there's a second angle that also works, because there are some triangles that can work with two different angle measures. And we know on the unit circle, if I were to draw this, that any angle measure here and its symmetric angle over here would have the same y coordinate, which means they have the same sine value. So there's another angle that would also give us sine of C equal to 0.4727. And the way that we're going to get that is we're always going to do either pi minus the original angle if we're in radians, or 180 minus the original angle if we're in degrees. So just to recap here, there's two angles that have the same sine value, and our calculator only gives us the first one right here. So we always have to find the second one. And if we're in degrees, we'll do that by doing 180 minus the first angle. If we're in radians, we'll do that by doing pi minus the first angle. So if I do 180 minus the 28.2, that gives me 151.8, which we can round to 3 sig figs, 152. So in order to check, do I have two answers to this question, I need to double check and see if that could work. And so my question is, knowing that I already have an angle here that's 100 degrees, could I have this angle here be 152 degrees? And hopefully you're thinking about your triangle rules and remembering that a triangle's interior angles have to add up to 180. And if we add up 100 and 152, that gives us 252, which is way more than 180. So it turns out that this second angle won't work, and this is our only answer. However, every time you do a sine rule to solve for an angle, you always need to check that second angle. And a lot of times with IB, if they are going to have you have two answers, like if they know that the triangle has that, instead of saying find BCA, they might have said find the possible angles, plural, of BCA. And so they usually leave little clues like that to indicate that you're going to get two solutions. So that's a good way to kind of check. But you always have to find out if you have another angle there. Okay, so here's a problem that doesn't have a triangle drawn for us, so we're going to draw it. When you draw the triangle, it truly does not matter what your triangle actually looks like, because we're not necessarily drawing it to scale, we're just labeling it correctly. So I'm going to label my triangle ABC. we know AB is 6 centimeters and AC is 8 centimeters. And we know that the area is 16 centimeters squared. Find the two possible values, so we should make sure that we're getting two answers, for angle A. So this is the angle we're solving for. So there are two formulas for the area of a triangle, 1/2 base times height, but we don't know that we have a base and a height per se. So the other one is 1/2 AB sine of C, which requires us to know two sides and the angle between it. And in this case, we have the two sides, and we're trying to find this angle between it, and we have the area. So we can actually substitute in to solve. So we know the two sides are 6 and 8, and the angle between it is angle A. So I'm going to label it angle A, and we know the area is 16. So when I do that, I am going to get 16 equals 24 sine of A, which gives us 2/3 equals sine of A. And so I am going to take sine inverse of 2/3 to find out what angle A is. And since they didn't clarify whether it's whether we're in degrees or in radians, they don't seem to care. We can put our answer in either one. I'm just going to go ahead and leave my answer, or my calculator, which is in degree mode. So when I do that, I get angle A is 41.8103 ... degrees. Now, the question specifically said, find the two possible values of A. Just like the last problem, whenever we're taking sine inverse, our calculators, and we're using our calculators to do so, our calculators are only giving us this first angle. But there's that symmetric one right there that we need to be able to come up with. And so again, same rule for sine. We're going to do 180 minus theta. I'm going to do 180 minus that 41.8103 ... And when I do that, it will give me my second possible angle. And if it was 189. Okay, so I can answer them by rounding to 3 sig figs. So 138 degrees or 41.8 degrees. And so those are our two possible values. Then it says, given that angle A is obtuse, find BC. So now we are to assume that angle A is obtuse, so that tells us that we can move forward with this problem as if angle A is 138 degrees. And so now we can go ahead and find length BC. When I think about whether I'm using sine rule or cosine rule, I don't have a matching set, angle and side, so that puts me at using cosine rule. And the angle that we know is 138 degrees, because again, we're assuming that it's the obtuse one. The other two sides are 6 and 8. And then we are going to solve for C. And so we get C squared equals 171.34 ... Take the square root of both sides. And that gives us that C, rounded to 3 sig figs, is 13.1. And I think the units were centimeters, but I'm going to double check. Yes, centimeters. Okay, so take a look at this problem and give it a try, and then, so pause the screen and then come back to it. And as I work this one, so they gave us the drawing of the triangle on this one. They always double check. I know that a lot of times they label the information, but always read through the problem and make sure, because sometimes they don't label everything. So make sure everything they wrote in the text is labeled on here, because they don't always do that. So it says RQ equals 9, so they labeled that one. PRQ equals 70, so they did label that one. PQR equals 45, so they labeled all three. So the first question asks us to find the remaining angle, RPQ. And this one doesn't require anything fancy. It just requires us to remember that all three angles in a triangle, all interior angles, should add up to 180. So 70 plus 45 plus angle RPQ should equal 180. And so we can find it just simply by subtracting. And that leaves us RPQ as 65 degrees. And then the second part asks us to find PR. And before I do that, I'm going to go ahead and label this as 65. Okay, so PR, that is right here. And we ask ourselves, can we use sine rule or do we need to use cosine rule? Well, we do actually have this matching set, 65 degrees and 9. And then this partially complete set, 45 degrees, and the side we're trying to find. So we can use sine rule. So we're going to set that up. Q, which is length PR, right? That's the side across from angle Q, would be to sine of 45 degrees as 9 is to sine of 65 degrees. And so we can go ahead and multiply both sides by sine, that's 9, sine of 45. And that gives us that Q equals 7.02 centimeters. And we know Q is PR, so. Okay, and then part 4C asked us to find the area of angle PQR. And so that, again, we don't know the base and the height, so we're going to use that 1/2 AB sine of C. All we need to know for that is two sides and the angle between them. So the two sides that we know, this is 7.02, are 7.02 and 9. So the angle that we put for C has to be the angle that's between 7.02 and 9. So it's this angle here at 70 degrees. And so we can just use our calculators here, 0.5 times 7.02 times 9 times sine of 70. And that gives us 29.7 when we round to three significant figures. And our units there will be centimeters squared. Okay, we're going to look at one more question that has a circle. We've reviewed some problems that use sine rule and cosine rule and the area of a triangle. So looking at this one, it asks us to consider the following circle with center O for origin and radius of 6.8. It tells us the length of the arc, so we can say that length of arc PQR is 8.5. And if you were wondering why they call it PQR and not PR, it's because that's what makes it clear that it is this arc length and not this one right here. Because it could be either if they didn't specify that it went from P to Q to R, that it's this one. We know the formula for the length of an arc is theta times R. And that theta is what we are trying to find. We know the radius is 6.8. And actually, we know that the length of the arc is 8.5. And so we can solve for theta by just dividing 8.5 by 6.8. And that gives us 1.25 radians. Make sure that you are aware that anytime we are talking about this formula, we're talking about theta in radians. And so then it asks us to find the area of the shaded region. So that's an area of a sector. It's just a sector that's very large, this area, this shaded region here. And there are going to be two main strategies to do this. One strategy is to find the entire area of the circle and subtract this sector. And the other is to take the entire amount of radians in a circle, which is 2 pi, and subtract this angle here to get the angle of this big sector here. So you can do it either way. I'm going to go ahead and take pi r squared, the area of the circle, pi times r, which is 6.8 squared. And when I do that, that gives me 145.2672443 centimeters squared. And I'm going to find the area of this sector. I'm just going to call that x. And so we know that the area of the sector, which I'm calling x, is going to be equal to, and you're going to pull this formula right off your formula sheet, 1/2 times theta r squared. And we already solved theta to be 1.25. We know the radius to be 6.8. So we can find the area of the sector to be 1/2 times 1.25 times 6.8 squared. So that's 28.9 centimeters squared. And so what we know is that the whole area of the circle is that 145 number. The area of this sector here is 28.9. So the area of the shaded region is going to just be the difference. So that 145.267 minus the 28.9. And when I do that, that gives me 116 when you round to three significant figures, so that's 116 centimeters squared. One thing to note when you're working with stuff like this, it's really helpful if you label what you're solving for, so the area of a circle, the area of a sector. You can just write it as a subscript just like that as a way of keeping yourself organized and also helping the grader follow your work. If you're looking to do some extra practice problems on this, Chapter 10 of our Cambridge Math SL book is where you'll find them. 10B is the sine rule problems, 10C for cosine rule problems, 10D for the area of the triangle problems, and then 10F is your length of an arc problems, 10G is the area of the sector problems, and then 10H is the best place to go for problems that encompass the triangles and the circles all together, how you're most likely to see them on the IB exam.